Now, question 9. Let me read this problem for you. The diagram illustrates the position of particles in a progressive sound wave at one instant in time. The speed of the wave is v. P and Q are 2 points in the wave, a distance L apart. What is the expression for the frequency of the wave? And give the options in terms of this length and the speed of this wave. So let's pause right here and review a couple things related to sound waves. So sound waves, they are mechanical waves, which means they require particles in the medium to carry its energy. It could be liquid, like water, air, as gas, solid, like any material that is solid. All the particles that make up this medium, they are going to carry the sound energy. So it's considered a mechanical energy because it requires a carrier to move the energy, in this case here, from left to right. Also, sound waves, they are longitudinal waves, which means that the particles in the median, they are going to move to the right, to the left, to the right, to the left, or more common term, back and forth with the direction of the motion of the wave. So the wave is going, in this case here, from left to right. So the particles in the median, I can spot 2 here, is just vibrate in parallel with the direction, right? So if the direction is this way, so it's going to vibrate parallel with the direction. Now, because of this, the vibration, what makes is the particles, they bump into each other and make the other. This one is vibrating, this one is vibrating, this one is close by, so now this is vibrating and the adjacent particle is going to have the same type of motion. So what happened is, because of this type of behavior, we have 2 very specific areas in a longitudinal wave, which is an area where we have a concentration of particles and an area that is more relaxed, another one with more concentration, another one is more relaxed. And also we can say higher pressure, lower pressure, because you have less particles here, more particles, more pressure. So those areas, they are considered as high pressure, low pressure, alternating this way. And but what we call actually is this area that is more concentrated, is called compression, and this one rarefaction. Now, how we determine the wavelength, period, and the speed of one wave like this? How we're gonna spot the crest, how we're gonna spot the troughs, is kind of tricky. In this case, usually problems is going to kind of help and determine where is the location of a trough or a crest. But in this case here, the wavelength can be measured between 2 compressions or 2 rarefactions area. So you just need to spot the center. So the center of a compression with the center of the other compression, we have one complete wavelength. Or the center of a rarefaction with the center of another rarefaction, so we have a wavelength. Before leaving this page, I just want to show that a longitudinal wave usually is translated to a transverse wave form, even though it's not a transverse wave. But because it's way easier to identify the wavelength, the crest, the troughs, the period, the frequency, for the reason is way easier, the resting line, than one wave like this. So back to our problem, the wave here is being represented by the dot uniform. So this picture shows particles in a longitudinal wave. At P, we have here an area of compression, and Q looks like is rarefaction. So because the particles are more spaced out from each other. So a wavelength in a longitudinal wave can be measured between two consecutive compressions or two consecutive rarefaction. So therefore, L is the distance between a compression and a rarefaction. So in complete wavelength, you'll be 2L. For example, because the distance here is between a compression and rarefaction, so our L here is 4.5 centimeters. So that's the L. A complete wavelength, you'll be a distance between two consecutive compression areas. So if this is our compression and this is rarefaction, so our another compression will be 4.5, so about here. So this here will be our complete wavelength between compression with compression. Okay, what that means is the wavelength is 2 times L, because that will be the complete wavelength. The formula, the wave formula is just this one, frequency times its wavelength. So the problem here, the options, they all show or L or V, not frequency. So let's solve these in terms of the frequency. There you go. So now F is V divided by lambda, and lambda is 2L. So this is expression right here corresponds to A. So that is the final answer. So let's read question 10. In an experiment to determine the wavelength of sound in air, a stationary wave is set up in an air column. The distance between a node and an adjacent antinode is L. What is the wavelength of the sound? So let's sketch a diagram to understand this. So this is our air column. So let's flip like this to make it easy to draw. So let's assume that in this opening we have a antinode, which is 1/4 of a wavelength. And then we have, if it is 1/4, this distance here will be another 1/4, and the distance another one. So this will be our next node. So our next node will be, so the wave go like this, right? And comes back because it's a stationary wave. Okay. And then it can keep going. Go like this, and somehow it's gonna come back like this, because that is the shape of a stationary wave. This is the shape of a stationary wave in an air column. Next, let's identify node and antinode. You don't have actually to make a long wave like I did, but that's fine. So here you have antinode, here we have a node, here we have antinode, here we have a node, here we have an antinode. So because usually stationary waves, they are symmetrical, so doesn't matter where you're gonna pick, because let's follow the information right here. The distance between a node and an adjacent antinode is L. So node and antinode, doesn't matter which one you are gonna pick. Let's say this one here, between a node and adjacent antinode. So this distance is L. So based on this, what is the wavelength of the sound? Now we have this wavelength right here, just one, and this is the reflected one, and both together form a stand wave. Now, our node is here, node, that is no vertical displacement, no, no, no. And we have in the center here, we have the antinode. So if it is a complete wavelength, this section here, if you divide in 4 parts, so each part corresponds to 1/4 of a wavelength. So one complete wavelength is 1/4 plus 1/4 plus 1/4 plus 1/4. Okay, that gives you a complete wavelength. Now the distance between a node and antinode here, now we can see is 1/4. The distance between two nodes, two consecutive nodes, is half of a wavelength. So that's what I want that you see the wavelength in terms of the length of this wave. Now from this diagram, the distance between a node and adjacent antinode is just 1/4 of the wavelength. Likewise is this. So the distance between a node and antinode is 1/4 of a wavelength, which means this L is equal 1/4 of the wavelength. So to figure out the length of a wavelength, so we have to add 1/4 4 times. So 1/4 will be L plus L plus L plus L, which should be 4L. So L, 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 L gives us 4L, and this is the correct answer. Question 11. In one of the first experiments to demonstrate the Doppler effect, a train was filled with trumpets. All play a note of frequency 440 Hertz. The difference in observed frequency of the note as the train directly approached a stationary observer was 22 Hertz. The speed of the sound was 340 meters per second. At which speed was the train moving? So this is our Doppler effect formula. For paper 1 and paper 2, the observer usually is at rest or stationary. So VO is 0. So now let's match the story with this diagram. So here is a moving train with sound from trumpets that is being emitted while the train is moving toward an observer. The frequency emitted is 440 Hertz. The problem is looking for the speed of the sound source, which is in the train, so the speed of the train. Now we have an observer that is stationary, so the speed of the observer is 0, and the frequency the observer receives says here there's the difference in observed frequency of the note as the train directly approached a stationary observer was 22 Hertz. So let's take a closer look on the information from this problem. The difference in observed frequency was 22 Hertz. So I place this box here for we kind mathematically determined, or you can do mentally, but if you like to see numbers put together, so pay attention on this. So the difference observed is equal to the frequency observed minus the frequency emitted. So that's the difference. The problem was provided. FO minus emitted is 440 Hertz. So FO is 22. This is negative. Go to the other term, positive. So when you add those, the frequency observed is 462 Hertz. So now let's replace our values. So FO is 462 hertz is equal to FE is 440. The speed of sound in the air, see the air, is 340. V and V is the same value. VO is 0 because the observer is stationary. And VS is what the problem is asking. To determine if it's positive or negative here on the denominator of this fraction, you have two options. One is memorizing this. So here we have the source moving toward the observer. So VS is negative. So to finalize this question, the rest is just basic algebra. So here we have the sequence that I did. I moved 440 to the other side of the equation, and that's the result. I multiply here, and I play around with the signs, and that's the final answer. And if you are going to look the option that kind of matches with this, it will be 16.2 meters per second. Beautiful problem.